Every morning, a nuclear furnace 93 million miles away floods our world with the precise energy that makes life possible. But what if that gentle yellow star suddenly vanished, replaced by objects so strange they challenge the very fabric of reality itself? What if the cosmos decided to conduct the ultimate experiment in destruction, swapping our life-giving sun with black holes that devour light, neutron stars denser than atomic nuclei, or theoretical constructs that bend space and time beyond recognition? 1. The cosmic thought experiment. In the depths of space, where temperatures approach absolute zero and matter behaves in ways that mock our earthly understanding, modern astronomy has unveiled a menagerie of objects so bizarre they seem torn from the pages of science fiction. Yet these cosmic monsters are not mere fantasy. They are the documented children of stellar death, the inevitable endpoints of gravitational collapse, and the testing grounds where the universe experiments with the fundamental limits of physics itself. Our sun, that familiar golden disk that has illuminated human civilization for millennia, appears almost mundane by comparison. A middle-aged yellow dwarf star, neither particularly large nor especially small, it burns hydrogen with the steady reliability of a cosmic metronome. For 4.6 billion years, it has maintained the delicate balance that keeps Earth neither frozen nor scorched, providing exactly 1,361 watts per square meter of life-sustaining energy. Yet this apparent ordinariness masks an extraordinary precision, a stellar Goldilocks zone of mass, temperature, and composition that makes complex chemistry, liquid water, and ultimately life itself possible. But what if the cosmic dice had rolled differently? What if some incomprehensible force could reach across the void and substitute our gentle sun with the universe's most extreme objects? The very question opens doorways into realms where Einstein's relativity becomes not abstract theory but visceral reality, where quantum mechanics operates on astronomical scales, and where the comfortable laws of physics transform into instruments of cosmic terror. Modern telescopes have become time machines, peering into the depths of space to catalog objects that challenge our understanding of what matter can become under extreme conditions. The Event Horizon Telescope has captured images of supermassive black holes devouring light itself at the centers of distant galaxies. The LIGO-Virgo gravitational wave detectors have recorded the space-time ripples created when neutron stars, objects so dense that a teaspoon would weigh as much as Mount Everest, spiral into each other at a significant fraction of light speed. The James Webb Space Telescope has directly observed the birth of these cosmic extremes, watching as massive stars collapse into objects where the normal rules of reality simply cease to apply. Each discovery adds another entry to the universe's catalog of impossibilities made real. Magnetars with magnetic fields quadrillion times stronger than Earth's, so powerful they could stretch atoms into needle-thin shapes and disrupt the quantum vacuum itself. Strange stars composed of exotic quarks that might convert any matter they touch into their own alien substance. Theoretical boson stars that exist as single macroscopic quantum objects held together by their own gravity. Wormholes that could connect distant regions of spacetime through tunnels that bypass the conventional three dimensions of space. These objects represent the universe's capacity for extremes, conditions where space and time become curved beyond recognition, where matter reaches densities that compress atomic nuclei until they touch, where energy densities approach those that existed in the first moments after the Big Bang. They are the products of stellar death, gravitational collapse, and physical processes so violent they can sterilize entire regions of galaxies. Yet perhaps most remarkably, the mathematics that describes these cosmic monsters allows us to calculate with startling precision what would happen if any of them suddenly appeared in our solar system. The equations of general relativity, quantum field theory, and thermodynamics provide the tools to map out humanity's fate hour by hour, minute by minute, in scenarios ranging from gradual climate death to instantaneous annihilation. The replacement of our sun represents more than a thought experiment. It becomes a lens through which we can examine the fundamental forces that govern reality itself. How would Earth's orbit change around a solar-mass black hole? What would the sky look like during the final moments before a magnetar's radiation sterilized our planet? Could any form of life survive the gradual cooling of a white dwarf star? How long would technological civilization persist in the electromagnetic chaos surrounding a pulsar? Recent scientific breakthroughs have transformed these questions from pure speculation into quantitatively precise predictions. The LIGO-Virgo collaboration announced their 200th gravitational wave detection in March 2025, providing exact measurements of neutron star properties and black hole behaviors. The Event Horizon Telescope's 2022 image of Sagittarius A*, the supermassive black hole at our galaxy's center, revealed magnetic field structures that inform our understanding of how these objects interact with their surroundings. The James Webb Space Telescope's July 2024 detection of neutron star emission from supernova remnant SN 1987A confirmed theoretical models of stellar collapse and the birth of these extreme objects. Each observation adds another piece to the puzzle of cosmic destruction, allowing astronomers to predict not just what these objects look like, but exactly how they would reshape reality in our solar system. The mathematics of doom has become as precise as the mathematics of orbital mechanics, temperature gradients, and electromagnetic field interactions. But perhaps the most profound revelation from contemplating these cosmic replacement scenarios lies not in their capacity for destruction, but in what they reveal about the extraordinary precision required for life's existence. Our sun provides not merely energy, but precisely the right amount of energy at exactly the right wavelengths, delivered with remarkable stability over billions of years. Its mass creates gravitational conditions that maintain stable planetary orbits without tidal disruption. Its magnetic field shields us from galactic cosmic rays, while allowing beneficial solar-wind interactions that help maintain our atmosphere. The universe operates according to physical laws that permit both creation and destruction on scales beyond human comprehension. Stars forge the heavy elements necessary for planets and life, but their deaths create objects so extreme they sterilize vast regions of space. The same gravitational collapse that creates neutron stars and black holes also powers the energetic processes that distribute heavy elements throughout galaxies, seeding future generations of planetary systems. In replacing our gentle yellow star with the universe's strangest objects, we embark on a journey to the limits of physics itself, a voyage that will reveal not pathways to survival, but deeper appreciation for the cosmic lottery that placed us in orbit around a perfectly ordinary, perfectly stable, perfectly life-sustaining star. The mathematics of survival and the physics of destruction await, ready to guide us through scenarios where reality itself becomes unrecognizable. What follows is not merely an exercise in cosmic catastrophe, but an exploration of the fundamental forces that shape our universe, the delicate balance that makes life possible, and the profound fortune that allows us to contemplate these mysteries from the safety of our privileged cosmic address. Prepare to witness the power of physics unleashed, where the strangest objects in the universe reveal the true meaning of cosmic terror. 2. Black holes. Regions where reality breaks down. The most terrifying possibility in our cosmic thought experiment begins not with violence, but with silence. If our sun were suddenly replaced by a black hole of identical mass, the first sign of this ultimate catastrophe would be the most subtle. Gravity would continue to work exactly as before. Earth would maintain its precise 365-day orbit. The moon would continue its familiar dance around our planet. And for exactly 8 minutes and 20 seconds, sunlight would still warm our world as if nothing had changed. Then, as the last photons completed their 93 million-mile journey from a star that no longer existed, eternal darkness would descend upon a world whose fate had already been sealed. Black holes represent the universe's most extreme solution to the problem of matter under extreme gravitational stress. When the nuclear furnaces that power stars finally exhaust their fuel, gravity, patient and relentless, begins its final victory. For stars massive enough to overwhelm every quantum mechanical force that attempts to resist collapse, the result is an object so dense that it punches a hole in the fabric of spacetime itself. At the center lies a singularity where density becomes infinite and the laws of physics break down completely. Surrounding this impossible point stretches the event horizon, a spherical boundary beyond which nothing, not even light itself, can escape. The mathematics of black hole formation reveal a universe far stranger than our everyday experience suggests. Karl Schwarzschild's solution to Einstein's field equations, derived in 1916 while serving on the Russian front during World War I, described objects so bizarre that even Einstein initially refused to believe they could exist in nature. The Schwarzschild radius, the critical distance where escape velocity equals the speed of light, defines the event horizon's location. For a solar mass black hole, this boundary extends merely 3 kilometers from the center, creating a sphere small enough to fit within a city block yet massive enough to bind the fate of planets orbiting millions of kilometers away. Recent observations have shattered our understanding of black hole demographics across the universe. The smallest confirmed stellar black hole, discovered in the X-ray binary system 2 mass J05215658 plus 4359220, weighs just 3.3 solar masses, barely above the theoretical minimum mass required for black hole formation. At this boundary, the distinction between neutron stars and black holes becomes critically important. Neutron degeneracy pressure can support objects up to approximately 2.17 solar masses, but beyond this limit, no known force in the universe can prevent total gravitational collapse. The formation process of stellar mass black holes requires a cosmic drama of staggering proportions. When a star at least 25 times more massive than our Sun exhausts its nuclear fuel, the core temperature rises to billions of degrees as the star attempts to fuse increasingly heavy elements. Iron represents the end of this process. Fusing iron actually absorbs energy rather than releasing it, causing the core to collapse catastrophically in less than a second. The infalling matter reaches speeds of 70,000 kilometers per second before rebounding off the incompressibly dense core, creating a supernova explosion visible across billions of light-years. Yet, if the core mass exceeds the neutron degeneracy limit, not even this cosmic detonation can prevent the formation of a black hole. At the opposite extreme of the mass spectrum lurk supermassive black holes with masses reaching billions of times our Sun's. The Event Horizon Telescope's groundbreaking 2019 image of M87** revealed a black hole weighing 6.5 billion solar masses, its event horizon spanning 120 astronomical units, larger than Pluto's orbit around our Sun. Even more remarkably, the May 2022 image of Sagittarius A**, the supermassive black hole at our galaxy's center, showed organized magnetic field structures surrounding a 4-million solar mass monster lurking just 26,000 light-years from Earth. The discovery of intermediate mass black holes has filled a puzzling gap in the cosmic census. These objects, ranging from 100 to 100,000 solar masses, represent the missing link between stellar mass black holes formed from individual star collapse and supermassive black holes that anchor galaxy centers. The LIGO-Virgo collaboration's detection of GW 190521 in May 2020 provided the first confirmed observation of intermediate mass black hole formation, revealing a 142 solar mass object created from the merger of 85 and 66 solar mass progenitors. The event released energy equivalent to 8 solar masses in gravitational waves during a merger lasting less than 0.1 seconds. But what would happen if any of these cosmic monsters suddenly appeared in our solar system? The answer defies popular misconceptions about black holes as cosmic vacuum cleaners. Contrary to science fiction portrayals, a solar mass black hole would not dramatically alter planetary orbits at all. Newton's shell theorem and Einstein's general relativity both confirm that gravity depends only on mass and distance, not on whether that mass is distributed as a normal star or compressed into a point. Earth would continue its familiar orbit exactly as before, neither spiraling inward nor flying away into interstellar space. The true catastrophe would begin with the sudden cessation of nuclear fusion energy. Our Sun converts 4.26 million tons of matter into energy every second, flooding the solar system with 3.8 times 10 superscript 2 watts of power. A black hole produces no such energy through fusion. It can only release energy by converting the gravitational potential energy of infalling matter into heat and radiation through the formation of an accretion disk. Without a continuous supply of material to feed upon, a solitary black hole would remain essentially invisible and cold. The timeline of Earth's destruction would unfold with mathematical precision. Photosynthesis would cease within hours as chlorophyll molecules exhausted their stored light energy. Surface temperatures would begin dropping immediately as Earth's atmosphere radiated heat into space without solar input to replenish it. Within days, average surface temperatures would fall below freezing. Within weeks, the greenhouse effect would collapse as carbon dioxide began condensing into dry ice at the poles. Atmospheric collapse would accelerate as nitrogen and oxygen liquefied, leaving only a thin residual atmosphere of noble gases. Yet this scenario might paradoxically offer the longest potential survival time among exotic sun replacements. Deep subsurface ecosystems already exist around hydrothermal vents, demonstrating life's ability to survive without solar energy. These communities derive energy from chemosynthesis, using chemical reactions involving hydrogen sulfide, methane, and other compounds to power biological processes. Earth's radioactive decay provides approximately 4.4 times 10 superscript 1 superscript 3 watts of geothermal energy, less than 0.03% of solar input, but sufficient to maintain liquid water in localized underground environments for millions of years. The visual transformation would be both gradual and terrifying. The black hole itself would remain invisible unless it acquired an accretion disk from remaining solar system material. Gravitational lensing would bend light around the event horizon, creating multiple distorted images of background stars and producing Einstein rings, perfect circles of light from objects directly behind the black hole. The night sky would become a surreal gallery of stretched and duplicated stellar images, with some stars appearing to dance in impossible patterns as their light followed curved paths through warped spacetime. If the black hole did acquire matter, perhaps from the solar wind, cometary material, or debris from disrupted asteroids, the resulting accretion disk would create one of the universe's most spectacular and deadly phenomena. Matter spiraling into a black hole can reach temperatures exceeding 10 million Kelvin, glowing brilliant white-hot and potentially outshining our original sunday. The disk would appear as a glowing ring around the black hole's dark shadow, with relativistic effects causing one side to appear much brighter than the other due to Doppler boosting of light from matter moving toward Earth at significant fractions of light speed. The magnetic fields generated within accretion disks can launch relativistic jets, narrow beams of particles and energy extending thousands of times the black hole's diameter. If Earth lay in the path of such a jet, the high-energy radiation would sterilize our planet's surface within seconds, while the electromagnetic pulse would permanently destroy all electronic technology. Even scattered radiation from jet interactions with interstellar matter could prove lethal across solar system distances. Perhaps most unsettling of all, the black hole's gravitational field would create measurable but invisible effects on spacetime itself. Clocks would run slightly slower near the event horizon due to gravitational time dilation, an effect that becomes extreme close to the black hole but remains detectable even at planetary distances. GPS satellites orbiting a black hole would require constant adjustments for relativistic effects that would gradually accumulate into significant errors. The Hawking radiation emitted by a solar mass black hole presents its own cosmic irony. Stephen Hawking's calculations show that black holes emit thermal radiation with a temperature inversely proportional to their mass. A solar mass black hole would have a temperature of approximately 6 times 10 Kelvin, far colder than the cosmic microwave background radiation permeating the universe. Rather than evaporating through Hawking radiation, such a black hole would actually grow by absorbing the warmer background radiation, gaining mass over cosmic timescales. This scenario reveals the profound precision required for life's existence. The universe has produced objects representing the ultimate expression of gravitational power, regions where matter becomes so dense it literally tears holes in the fabric of reality itself. Yet the same physical laws that permit such cosmic violence also allow the gentle nuclear fusion that has powered our sun's steady warmth for billions of years. In contemplating the replacement of our life-giving star with a gravitational monster, we begin to appreciate the extraordinary fortune that placed us in orbit around a perfectly ordinary, perfectly stable nuclear furnace rather than a cosmic abyss that devours light itself. But black holes represent merely the beginning of our journey into cosmic extremes. Far stranger objects await, neutron stars where matter reaches densities that compress atomic nuclei until they touch, creating cities of nuclear matter where physics operates according to rules that challenge our deepest understanding of reality itself. 3. Neutron stars. Cities of impossible matter. If black holes represent regions where matter vanishes beyond the cosmic censorship of event horizons, neutron stars embody the opposite extreme, matter compressed to such impossible densities that a city-sized sphere contains more mass than our entire sun. Here, the universe conducts its most violent experiments in nuclear physics, creating objects where a single teaspoon of material would weigh as much as Mount Everest, and where the boundary between individual particles dissolves into a crystalline lattice of pure nuclear matter. The birth of a neutron star requires a cosmic catastrophe of unimaginable proportions. When a star between 8 and 25 solar masses exhausts its nuclear fuel, the core collapse occurs so rapidly that protons and electrons are literally crushed together, forced to overcome their electromagnetic repulsion and merge into neutrons. In less than a second, a sphere of ordinary matter the size of Earth compresses to a ball barely 20 kilometers across, while the outer layers explode outward in a supernova that can briefly outshine an entire galaxy containing hundreds of billions of stars. The physics governing neutron star interiors pushes matter into states that exist nowhere else in the observable universe. At the surface, densities reach 10 superscript 1 grams per cubic centimeter, roughly 100 million times denser than water and approaching the density of atomic nuclei themselves. But this represents merely the beginning of the neutron star's assault on conventional physics. Deeper within, matter may transition through phases that theoretical physicists can barely comprehend. Hyperons containing strange quarks, kaon condensates, and potentially even free quark matter where individual particles lose their identity entirely. Recent observations have pushed the boundaries of what neutron stars can become before collapsing into black holes. The pulsar PSR J0740 plus 6620 weighs 2.35 solar masses, dangerously close to the theoretical maximum known as the Tolman-Oppenheimer-Fokoff limit. At such masses, neutron degeneracy pressure struggles against gravitational collapse, with the outcome determined by the equation of state of matter at nuclear densities. The fact that such massive neutron stars exist suggests exotic matter phases in their cores, possibly including strange quarks or other particles that don't exist in normal terrestrial matter. The James Webb Space Telescope achieved a historic breakthrough in July 2024 when it detected direct evidence of neutron star emission from supernova remnant SN 1987A, ending a 37-year search since the supernova's initial observation. Webb identified every morning, a nuclear furnace 93 million miles away floods our world with the precise energy that makes life possible. But what if that gentle yellow star suddenly vanished, replaced by objects so strange they challenge the very fabric of reality itself? What if the cosmos decided to conduct the ultimate experiment in destruction, swapping our life-giving sun with black holes that devour light, neutron stars denser than atomic nuclei, or theoretical constructs that bend space and time beyond recognition? 1. The cosmic thought experiment. In the depths of space, where temperatures approach absolute zero and matter behaves in ways that mock our earthly understanding, modern astronomy has unveiled a menagerie of objects so bizarre they seem torn from the pages of science fiction. Yet these cosmic monsters are not mere fantasy. They are the documented children of stellar death, the inevitable endpoints of gravitational collapse, and the testing grounds where the universe experiments with the fundamental limits of physics itself. Our sun, that familiar golden disk that has illuminated human civilization for millennia, appears almost mundane by comparison. A middle-aged yellow dwarf star, neither particularly large nor especially small, it burns hydrogen with the steady reliability of a cosmic metronome. For 4.6 billion years, it has maintained the delicate balance that keeps Earth neither frozen nor scorched, providing exactly 1,361 watts per square meter of life-sustaining energy. Yet this apparent ordinariness masks an extraordinary precision, a stellar Goldilocks zone of mass, temperature, and composition that makes complex chemistry, liquid water, and ultimately life itself possible. But what if the cosmic dice had rolled differently? What if some incomprehensible force could reach across the void and substitute our gentle sun with the universe's most extreme objects? The very question opens doorways into realms where Einstein's relativity becomes not abstract theory but visceral reality, where quantum mechanics operates on astronomical scales, and where the comfortable laws of physics transform into instruments of cosmic terror. Modern telescopes have become time machines, peering into the depths of space to catalog objects that challenge our understanding of what matter can become under extreme conditions. The Event Horizon Telescope has captured images of supermassive black holes devouring light itself at the centers of distant galaxies. The LIGO-Virgo gravitational wave detectors have recorded the space-time ripples created when neutron stars, objects so dense that a teaspoon would weigh as much as Mount Everest, spiral into each other at a significant fraction of light speed. The James Webb Space Telescope has directly observed the birth of these cosmic extremes, watching as massive stars collapse into objects where the normal rules of reality simply cease to apply. Each discovery adds another entry to the universe's catalog of impossibilities made real. Magnetars with magnetic fields quadrillion times stronger than Earth's, so powerful they could stretch atoms into needle-thin shapes and disrupt the quantum vacuum itself. Strange stars composed of exotic quarks that might convert any matter they touch into their own alien substance. Theoretical boson stars that exist as single macroscopic quantum objects held together by their own gravity. Wormholes that could connect distant regions of spacetime through tunnels that bypass the conventional 3 dimensions of space. These objects represent the universe's capacity for extremes, conditions where space and time become curved beyond recognition, where matter reaches densities that compress atomic nuclei until they touch, where energy densities approach those that existed in the first moments after the Big Bang. They are the products of stellar death, gravitational collapse, and physical processes so violent they can sterilize entire regions of galaxies. Yet perhaps most remarkably, the mathematics that describes these cosmic monsters allows us to calculate with startling precision what would happen if any of them suddenly appeared in our solar system. The equations of general relativity, quantum field theory, and thermodynamics provide the tools to map out humanity's fate hour by hour, minute by minute, in scenarios ranging from gradual climate death to instantaneous annihilation. The replacement of our sun represents more than a thought experiment. It becomes a lens through which we can examine the fundamental forces that govern reality itself. How would Earth's orbit change around a solar-mass black hole? What would the sky look like during the final moments before a magnetar's radiation sterilized our planet? Could any form of life survive the gradual cooling of a white dwarf star? How long would technological civilization persist in the electromagnetic chaos surrounding a pulsar? Recent scientific breakthroughs have transformed these questions from pure speculation into quantitatively precise predictions. The LIGO-Virgo collaboration announced their 200th gravitational wave detection in March 2025, providing exact measurements of neutron star properties and black hole behaviors. The Event Horizon Telescope's 2022 image of Sagittarius A*, the supermassive black hole at our galaxy's center, revealed magnetic field structures that inform our understanding of how these objects interact with their surroundings. The James Webb Space Telescope's July 2024 detection of neutron star emission from supernova remnant SN 1987A confirmed theoretical models of stellar collapse and the birth of these extreme objects. Each observation adds another piece to the puzzle of cosmic destruction, allowing astronomers to predict not just what these objects look like, but exactly how they would reshape reality in our solar system. The mathematics of doom has become as precise as the mathematics of orbital mechanics, temperature gradients, and electromagnetic field interactions. But perhaps the most profound revelation from contemplating these cosmic replacement scenarios lies not in their capacity for destruction, but in what they reveal about the extraordinary precision required for life's existence. Our sun provides not merely energy, but precisely the right amount of energy at exactly the right wavelengths, delivered with remarkable stability over billions of years. Its mass creates gravitational conditions that maintain stable planetary orbits without tidal disruption. Its magnetic field shields us from galactic cosmic rays, while allowing beneficial solar-wind interactions that help maintain our atmosphere. The universe operates according to physical laws that permit both creation and destruction on scales beyond human comprehension. Stars forge the heavy elements necessary for planets and life, but their deaths create objects so extreme they sterilize vast regions of space. The same gravitational collapse that creates neutron stars and black holes also powers the energetic processes that distribute heavy elements throughout galaxies, seeding future generations of planetary systems. In replacing our gentle yellow star with the universe's strangest objects, we embark on a journey to the limits of physics itself. A voyage that will reveal not pathways to survival, but deeper appreciation for the cosmic lottery that placed us in orbit around a perfectly ordinary, perfectly stable, perfectly life-sustaining star. The mathematics of survival and the physics of destruction await, ready to guide us through scenarios where reality itself becomes unrecognizable. What follows is not merely an exercise in cosmic catastrophe, but an exploration of the fundamental forces that shape our universe, the delicate balance that makes life possible, and the profound fortune that allows us to contemplate these mysteries from the safety of our privileged cosmic address. Prepare to witness the power of physics unleashed, where the strangest objects in the universe reveal the true meaning of cosmic terror. 2. Black holes. Regions where reality breaks down. The most terrifying possibility in our cosmic thought experiment begins not with violence, but with silence. If our sun were suddenly replaced by a black hole of identical mass, the first sign of this ultimate catastrophe would be the most subtle. Gravity would continue to work exactly as before. Earth would maintain its precise 365-day orbit. The moon would continue its familiar dance around our planet. And for exactly 8 minutes and 20 seconds, sunlight would still warm our world as if nothing had changed. Then, as the last photons completed their 93 million-mile journey from a star that no longer existed, eternal darkness would descend upon a world whose fate had already been sealed. Black holes represent the universe's most extreme solution to the problem of matter under extreme gravitational stress. When the nuclear furnaces that power stars finally exhaust their fuel, gravity, patient and relentless, begins its final victory. For stars massive enough to overwhelm every quantum mechanical force that attempts to resist collapse, the result is an object so dense that it punches a hole in the fabric of spacetime itself. At the center lies a singularity where density becomes infinite and the laws of physics break down completely. Surrounding this impossible point stretches the event horizon, a spherical boundary beyond which nothing, not even light itself, can escape. The mathematics of black hole formation reveal a universe far stranger than our everyday experience suggests. Karl Schwarzschild's solution to Einstein's field equations, derived in 1916 while serving on the Russian front during World War I, described objects so bizarre that even Einstein initially refused to believe they could exist in nature. The Schwarzschild radius, the critical distance where escape velocity equals the speed of light, defines the event horizon's location. For a solar mass black hole, this boundary extends merely 3 kilometers from the center, creating a sphere small enough to fit within a city block yet massive enough to bind the fate of planets orbiting millions of kilometers away. Recent observations have shattered our understanding of black hole demographics across the universe. The smallest confirmed stellar black hole, discovered in the X-ray binary system 2-mass J05215658 plus 4359220, weighs just 3.3 solar masses, barely above the theoretical minimum mass required for black hole formation. At this boundary, the distinction between neutron stars and black holes becomes critically important. Neutron degeneracy pressure can support objects up to approximately 2.17 solar masses, but beyond this limit, no known force in the universe can prevent total gravitational collapse. The formation process of stellar mass black holes requires a cosmic drama of staggering proportions. When a star at least 25 times more massive than our Sun exhausts its nuclear fuel, the core temperature rises to billions of degrees as the star attempts to fuse increasingly heavy elements. Iron represents the end of this process. Fusing iron actually absorbs energy rather than releasing it, causing the core to collapse catastrophically in less than a second. The infalling matter reaches speeds of 70,000 kilometers per second before rebounding off the incompressibly dense core, creating a supernova explosion visible across billions of light-years. Yet, if the core mass exceeds the neutron degeneracy limit, not even this cosmic detonation can prevent the formation of a black hole. At the opposite extreme of the mass spectrum lurk supermassive black holes with masses reaching billions of times our Sun's. The Event Horizon Telescope's groundbreaking 2019 image of M87** revealed a black hole weighing 6.5 billion solar masses, its event horizon spanning 120 astronomical units, larger than Pluto's orbit around our Sun. Even more remarkably, the May 2022 image of Sagittarius A**, the supermassive black hole at our galaxy's center, showed organized magnetic field structures surrounding a 4-million solar mass monster lurking just 26,000 light-years from Earth. The discovery of intermediate mass black holes has filled a puzzling gap in the cosmic census. These objects, ranging from 100 to 100,000 solar masses, represent the missing link between stellar mass black holes formed from individual star collapse and supermassive black holes that anchor galaxy centers. The LIGO-Virgo collaboration's detection of GW 190521 in May 2020 provided the first confirmed observation of intermediate mass black hole formation, revealing a 142 solar mass object created from the merger of 85 and 66 solar mass progenitors. The event released energy equivalent to 8 solar masses in gravitational waves during a merger lasting less than 0.1 seconds. But what would happen if any of these cosmic monsters suddenly appeared in our solar system? The answer defies popular misconceptions about black holes as cosmic vacuum cleaners. Contrary to science fiction portrayals, a solar mass black hole would not dramatically alter planetary orbits at all. Newton's shell theorem and Einstein's general relativity both confirm that gravity depends only on mass and distance, not on whether that mass is distributed as a normal star or compressed into a point. Earth would continue its familiar orbit exactly as before, neither spiraling inward nor flying away into interstellar space. The true catastrophe would begin with the sudden cessation of nuclear fusion energy. Our sun converts 4.26 million tons of matter into energy every second, flooding the solar system with 3.8 times 10 superscript 2 watts of power. A black hole produces no such energy through fusion. It can only release energy by converting the gravitational potential energy of infalling matter into heat and radiation through the formation of an accretion disk. Without a continuous supply of material to feed upon, a solitary black hole would remain essentially invisible and cold. The timeline of Earth's destruction would unfold with mathematical precision. Photosynthesis would cease within hours as chlorophyll molecules exhausted their stored light energy. Surface temperatures would begin dropping immediately as Earth's atmosphere radiated heat into space without solar input to replenish it. Within days, average surface temperatures would fall below freezing. Within weeks, the greenhouse effect would collapse as carbon dioxide began condensing into dry ice at the poles. Atmospheric collapse would accelerate as nitrogen and oxygen liquefied, leaving only a thin residual atmosphere of noble gases. Yet this scenario might paradoxically offer the longest potential survival time among exotic sun replacements. Deep subsurface ecosystems already exist around hydrothermal vents, demonstrating life's ability to survive without solar energy. These communities derive energy from chemosynthesis, using chemical reactions involving hydrogen sulfide, methane, and other compounds to power biological processes. Earth's radioactive decay provides approximately 4.4 times 10 superscript 1 superscript 3 watts of geothermal energy, less than 0.03% of solar input, but sufficient to maintain liquid water in localized underground environments for millions of years. The visual transformation would be both gradual and terrifying. The black hole itself would remain invisible unless it acquired an accretion disk from remaining solar system material. Gravitational lensing would bend light around the event horizon, creating multiple distorted images of background stars and producing Einstein rings, perfect circles of light from objects directly behind the black hole. The night sky would become a surreal gallery of stretched and duplicated stellar images, with some stars appearing to dance in impossible patterns as their light followed curved paths through warped spacetime. If the black hole did acquire matter, perhaps from the solar wind, cometary material, or debris from disrupted asteroids, the resulting accretion disk would create one of the universe's most spectacular and deadly phenomena. Matter spiraling into a black hole can reach temperatures exceeding 10 million Kelvin, glowing brilliant white-hot and potentially outshining our original sunday. The disk would appear as a glowing ring around the black hole's dark shadow, with relativistic effects causing one side to appear much brighter than the other due to Doppler boosting of light from matter moving toward Earth at significant fractions of light speed. The magnetic fields generated within accretion disks can launch relativistic jets, narrow beams of particles and energy extending thousands of times the black hole's diameter. If Earth lay in the path of such a jet, the high-energy radiation would sterilize our planet's surface within seconds, while the electromagnetic pulse would permanently destroy all electronic technology. Even scattered radiation from jet interactions with interstellar matter could prove lethal across solar system distances. Perhaps most unsettling of all, the black hole's gravitational field would create measurable but invisible effects on spacetime itself. Clocks would run slightly slower near the event horizon due to gravitational time dilation, an effect that becomes extreme close to the black hole but remains detectable even at planetary distances. GPS satellites orbiting a black hole would require constant adjustments for relativistic effects that would gradually accumulate into significant errors. The Hawking radiation emitted by a solar mass black hole presents its own cosmic irony. Stephen Hawking's calculations show that black holes emit thermal radiation with a temperature inversely proportional to their mass. A solar mass black hole would have a temperature of approximately 6 times 10 Kelvin, far colder than the cosmic microwave background radiation permeating the universe. Rather than evaporating through Hawking radiation, such a black hole would actually grow by absorbing the warmer background radiation, gaining mass over cosmic timescales. This scenario reveals the profound precision required for life's existence. The universe has produced objects representing the ultimate expression of gravitational power, regions where matter becomes so dense it literally tears holes in the fabric of reality itself. Yet the same physical laws that permit such cosmic violence also allow the gentle nuclear fusion that has powered our sun's steady warmth for billions of years. In contemplating the replacement of our life-giving star with a gravitational monster, we begin to appreciate the extraordinary fortune that placed us in orbit around a perfectly ordinary, perfectly stable nuclear furnace rather than a cosmic abyss that devours light itself. But black holes represent merely the beginning of our journey into cosmic extremes. Far stranger objects await, neutron stars where matter reaches densities that compress atomic nuclei until they touch, creating cities of nuclear matter where physics operates according to rules that challenge our deepest understanding of reality itself. 3. Neutron stars. Cities of impossible matter. If black holes represent regions where matter vanishes beyond the cosmic censorship of event horizons, neutron stars embody the opposite extreme, matter compressed to such impossible densities that a city-sized sphere contains more mass than our entire sun. Here, the universe conducts its most violent experiments in nuclear physics, creating objects where a single teaspoon of material would weigh as much as Mount Everest, and where the boundary between individual particles dissolves into a crystalline lattice of pure nuclear matter. The birth of a neutron star requires a cosmic catastrophe of unimaginable proportions. When a star between 8 and 25 solar masses exhausts its nuclear fuel, the core collapse occurs so rapidly that protons and electrons are literally crushed together, forced to overcome their electromagnetic repulsion and merge into neutrons. In less than a second, a sphere of ordinary matter the size of Earth compresses to a ball barely 20 kilometers across, while the outer layers explode outward in a supernova that can briefly outshine an entire galaxy containing hundreds of billions of stars. The physics governing neutron star interiors pushes matter into states that exist nowhere else in the observable universe. At the surface, densities reach 10 superscript 1 grams per cubic centimeter, roughly 100 million times denser than water and approaching the density of atomic nuclei themselves. But this represents merely the beginning of the neutron star's assault on conventional physics. Deeper within, matter may transition through phases that theoretical physicists can barely comprehend. Hyperons containing strange quarks, kaon condensates, and potentially even free quark matter where individual particles lose their identity entirely. Recent observations have pushed the boundaries of what neutron stars can become before collapsing into black holes. The pulsar PSR J0740 plus 6620 weighs 2.35 solar masses, dangerously close to the theoretical maximum known as the Tolman-Oppenheimer-Fokoff limit. At such masses, neutron degeneracy pressure struggles against gravitational collapse, with the outcome determined by the equation of state of matter at nuclear densities. The fact that such massive neutron stars exist suggests exotic matter phases in their cores, possibly including strange quarks or other particles that don't exist in normal terrestrial matter. The James Webb Space Telescope achieved a historic breakthrough in July 2024 when it detected direct evidence of neutron star emission from supernova remnant SN 1987A, ending a 37-year search since the supernova's initial observation. Webb identified highly ionized argon and energetic photons characteristic of neutron star surfaces, confirming theoretical models of stellar collapse and providing the first direct observation of these extreme objects emerging from stellar death. The detection revealed surface temperatures exceeding 1 million Kelvin and intense magnetic fields that accelerate particles to relativistic speeds. But what cosmic nightmare would unfold if such an object suddenly replaced our gentle sun? The scenario begins with immediate electromagnetic catastrophe. Young neutron stars radiate primarily in X-rays with surface temperatures reaching 10 million Kelvin, hot enough to generate luminosities equivalent to 2,000 suns. At Earth's orbital distance, this X-ray flux would deliver over 1 trillion watts per square meter, instantly lethal radiation levels that would strip away our planet's entire atmosphere through photoionization within minutes. The visual transformation would be both spectacular and terrifying. Unlike our sun's familiar disk spanning half a degree of sky, a neutron star would appear as an intensely bright pinpoint of blue-white light, roughly the angular size of a basketball viewed from several kilometers away. The surface gravity, 100 billion times stronger than Earth's, would be invisible to the eye but would fundamentally alter the behavior of matter and energy around the star. Light itself would struggle to escape the neutron star's gravitational well, emerging redshifted and time-dilated in ways that would create bizarre visual effects for any surviving observers. Most neutron stars manifest as pulsars, cosmic lighthouses that sweep beams of radio waves, visible light, and high-energy radiation across space as they rotate. The most rapidly spinning known pulsar, PSR J1748-2446 AD, completes 716 rotations per second, creating a stroboscopic nightmare that would turn day and night into concepts measured in milliseconds rather than hours. Each pulse would deliver a concentrated burst of lethal radiation, while the intervals between pulses would plunge Earth into darkness broken only by the faint glow of atmospheric gases heated by previous radiation doses. The discovery of the youngest known magnetar, Swift J1818.0-1607, in March 2020 revealed an object just 500 years old spinning once every 1.4 seconds. This finding challenged previous models suggesting magnetars should rotate much more slowly than typical pulsars, demonstrating that even our understanding of these extreme objects continues to evolve. The youth of this magnetar provides insights into the early evolution of neutron stars, when their rotation rates and magnetic field strengths reach maximum values before gradually declining over millions of years. Tidal forces around neutron stars would prove utterly catastrophic for any planetary system. The gravitational gradient across Earth's diameter would create tidal accelerations of approximately 2.4 times 10 superscript 3 meters per second squared, sufficient to tear our planet apart like a marshmallow in a blender. Earth would need to orbit beyond roughly 1 million kilometers to avoid complete tidal disruption, placing it at roughly 3 times the Moon's current distance from Earth. Even at such distances, the intense radiation environment would prove immediately fatal to all surface life. The magnetic field effects would add another layer of devastation. Neutron stars possess magnetic fields up to 1 trillion times stronger than Earth's, powerful enough to disrupt atomic bonds and modify the fundamental behavior of matter itself. These fields would interact catastrophically with Earth's magnetosphere, accelerating charged particles in our atmosphere to relativistic speeds and creating planet-wide aurora displays visible even through the deadly X-ray radiation. The electromagnetic induction effects would generate electrical currents powerful enough to melt metallic objects and permanently destroy all electronic technology within seconds. Neutron star surfaces exhibit properties that challenge our understanding of solid matter. The crystalline crust consists of atomic nuclei arranged in perfect lattices immersed in a sea of degenerate electrons, creating the strongest material in the universe with a tensile strength 10 superscript 1 times greater than steel. Occasional starquakes crack this crust as the neutron star's rotation gradually slows, releasing energies equivalent to magnitude 20 earthquakes, seismic events that would shatter continents if they occurred on Earth. The discovery of neutron star mergers through gravitational wave astronomy has revealed these objects' role as cosmic element factories. When 2 neutron stars spiral into each other, they create kilonovae, explosions that synthesize heavy elements through rapid neutron capture processes. The August 2017 detection of GW 170817 by LIGO Virgo provided the first direct observation of such a merger, revealing the creation of gold, platinum, and other heavy elements in quantities exceeding Earth's total mass. The James Webb Space Telescope's 2023 detection of tellurium from GRB 230307A marked the first direct observation of heavy element creation, confirming neutron star mergers as the primary source of elements heavier than iron in the universe. The rotation of neutron stars creates frame-dragging effects that would warp spacetime around our solar system. These objects spin so rapidly that they literally twist the fabric of space and time, creating gravitomagnetic fields that would cause gyroscopes to precess in directions impossible under Newtonian physics. The lens-throwing effect would gradually alter the orbital planes of planets, creating long-term instabilities that could eject worlds from the system over millions of years. Perhaps most remarkably, some neutron stars exhibit timing precision that rivals atomic clocks. Millisecond pulsars, spun up through accretion from companion stars, maintain rotational stability accurate to within a few microseconds over decades of observation. This precision results from the neutron star's enormous moment of inertia. A 20-kilometer sphere containing 1.4 solar masses resists changes in rotation with the stubbornness of a cosmic flywheel. If such an object replaced our Sun, it would serve as the ultimate timekeeper, marking Earth's final moments with metronomic precision. The electromagnetic pulse generated by a nearby neutron star would create cascading technological failures across human civilization. Radio communications would be overwhelmed by interference millions of times stronger than any terrestrial source. Satellite networks would fail as high-energy particles damaged electronics and altered orbital mechanics. Power grids would experience induced currents capable of melting transformers and causing permanent blackouts across entire continents. Even hardened military electronics designed to survive nuclear electromagnetic pulses would be destroyed within the first few seconds of neutron star radiation. Yet, among the universe's catalog of extreme objects, neutron stars represent merely another step toward ultimate cosmic violence. Beyond the realm of nuclear matter compressed to its breaking point lie objects where magnetic fields become so powerful they reshape the quantum vacuum itself. Magnetars that transform the space around them into realms where the fundamental forces of nature operate according to rules that exist nowhere else in the cosmos. 4. Magnetars, the universe's most powerful magnets. If neutron stars represent matter pushed to its absolute limit, magnetars embody magnetic fields so extreme they rewrite the rules of physics itself. These rare cosmic monsters, only 31 confirmed examples exist in our entire galaxy, possess magnetic fields quadrillion times stronger than Earth's, powerful enough to stretch atoms into needle-thin shapes, disrupt the quantum vacuum, and literally bend the trajectory of light through electromagnetic forces alone. They represent the universe's most violent marriage of matter and magnetism, where the boundary between classical physics and quantum field theory dissolves in a maelstrom of energy that defies human comprehension. The birth of a magnetar requires not merely the gravitational collapse that creates ordinary neutron stars, but a perfect storm of rapid rotation and convective dynamo processes during the first few seconds of neutron star formation. As the stellar core implodes, conservation of angular momentum spins the collapsing matter to rotation periods measured in milliseconds, while convective turbulence in the protoneutron star's superfluid interior amplifies magnetic fields through dynamo action. The result is a magnetic field strength approaching 10 superscript 1 Gauss, a trillion times stronger than the most powerful magnets humans have ever created, and so intense it approaches the quantum electrodynamic limit where the magnetic field itself begins to affect the structure of empty space. The discovery of Swift J 1818.0-1607 in March 2020 provided unprecedented insights into magnetar formation and evolution. This object represents the youngest known magnetar at approximately 500 years old, spinning once every 1.4 seconds, making it the fastest rotating magnetar ever observed. The finding challenged theoretical models suggesting magnetars should spin much more slowly than typical pulsars, revealing that these objects can maintain rapid rotation even while possessing magnetic fields strong enough to generate the most energetic explosions in the universe. To comprehend the true power of magnetar magnetic fields requires venturing into realms of physics where everyday intuition utterly fails. At field strengths exceeding 10 superscript 1 superscript 3 Gauss, the magnetic force becomes strong enough to overcome the electromagnetic bonds holding atoms together. Matter itself begins to behave in fundamentally different ways. Hydrogen atoms stretch into cylindrical shapes, with electron orbits compressed into thin rods aligned with the magnetic field lines. At magnetar strength fields approaching 10 superscript 1 Gauss, even the quantum vacuum begins to respond. Virtual particle pairs created by quantum fluctuations become polarized and can potentially transform into real particles, creating a phenomenon known as magnetic pair production. The electromagnetic chaos surrounding magnetars generates the most violent energy releases known in the universe. On December 27, 2004, magnetar SGR 1806-20 unleashed more energy in 1/10 of a second than our Sun emits in 100,000 years. The gamma-ray burst briefly saturated X-ray detectors across the solar system and temporarily brightened the object beyond the apparent magnitude of the full moon, despite lying 50,000 light-years from Earth. The burst released approximately 10 ergs of energy, equivalent to the gravitational binding energy of our Sun, in a stellar remnant no larger than Manhattan. But what cosmic nightmare would engulf our solar system if such an object suddenly replaced our life-giving Sun? The scenario would unfold as the most comprehensive electromagnetic apocalypse imaginable, beginning with effects that would make neutron star radiation seem gentle by comparison. The magnetar's magnetic field would instantly destroy all electronic systems on Earth through induced electromagnetic pulses millions of times stronger than nuclear weapons. The field's strength would be powerful enough to diamagnetically levitate living tissue. Human beings would experience forces attempting to tear apart the molecular bonds in their bodies. The visual spectacle would be simultaneously magnificent and terrifying beyond description. Massive coronal loops of plasma would arch millions of kilometers into space, guided by magnetic field lines more complex than any earthly aurora. These plasma structures would dwarf anything in our solar system, with individual magnetic flux tubes carrying more energy than the total output of human civilization. The magnetar's surface would crack periodically in starquakes as the magnetic field reconfigures, each event releasing gamma-ray bursts that would repeatedly sterilize Earth's surface, even if any life somehow survived the initial magnetic onslaught. The magnetic field interactions with Earth's magnetosphere would create electromagnetic phenomena beyond the scope of terrestrial experience. Charged particles in our atmosphere would be accelerated to relativistic speeds, creating planet-wide aurora displays visible across the entire electromagnetic spectrum from radio waves to gamma rays. The field strength would be sufficient to induce electrical currents capable of melting metallic structures and generating temperatures hot enough to ignite combustible materials through electromagnetic induction alone. Recent observations have revealed magnetars as sources of fast radio bursts, mysterious millisecond duration flashes that release as much energy as our Sun emits in several days. The April 2020 detection of a fast radio burst from SGR 1935 plus 2154 provided the first confirmed link between magnetars and these enigmatic signals, demonstrating that these objects can generate radio emissions 10 times brighter than typical pulsar signals. The burst mechanism likely involves magnetic reconnection events that accelerate particles to extreme energies, creating coherent radio emission through processes still not fully understood. The magnetic field geometry around magnetars creates some of the most complex plasma physics in the universe. Unlike the relatively simple dipole fields of ordinary neutron stars, magnetar fields exhibit multipolar structures with field lines that twist and reconnect in three-dimensional configurations of staggering complexity. These magnetic architectures can store enormous amounts of energy in stressed field configurations, which occasionally release through magnetic reconnection events that power the gamma-ray bursts and X-ray flares characteristic of magnetar activity. The quantum electrodynamic effects in magnetar magnetospheres push physics into regimes never achievable in terrestrial laboratories. At field strengths approaching the Schwinger limit of 4.4 times 10 superscript 1 superscript 3 Gauss, the quantum vacuum itself becomes birefringent electromagnetic waves with different polarizations travel at slightly different speeds, causing photons to effectively feel the magnetic field through quantum corrections to Maxwell's equations. This effect has been observed in the spectra of several magnetars, providing the first experimental confirmation of quantum electrodynamics predictions in the strong field regime. The rotational energy loss mechanisms in magnetars differ fundamentally from ordinary pulsars. While normal pulsars slow down gradually through magnetic dipole radiation, magnetars can experience sudden spin-up or spin-down events associated with starquakes that reconfigure the stellar crust and magnetic field geometry. These glitches can change the rotation period by microseconds in less than a second, representing sudden redistributions of rotational energy equivalent to millions of years of typical spin-down. The largest observed glitch in magnetar 1E2259 plus 586 changed its rotation period by 4 microseconds and was accompanied by X-ray emission increases lasting for months. The atmospheric composition around magnetars would be fundamentally altered by the intense radiation and magnetic fields. Ordinary atoms cannot exist in their ground states at magnetar surface conditions. Hydrogen and helium form magnetic polymers, where atoms bind in chain-like structures aligned with the magnetic field. The surface atmosphere consists of a thin skin of magnetized plasma where electrons are confined to cyclotron orbits with radii smaller than atomic dimensions, creating matter phases that exist nowhere else in the universe. Perhaps most terrifyingly, magnetar magnetic fields would interact with Earth's internal structure in ways that could trigger geological catastrophes. The rapid time-varying magnetic fields from magnetar flares would induce massive electrical currents in Earth's metallic core, potentially affecting the planet's magnetic field generation and creating electromagnetic coupling between the magnetar and our planet's interior. The field strengths would be sufficient to exert direct magnetic forces on iron-bearing materials in Earth's crust, potentially triggering earthquakes through magnetostriction effects. The electromagnetic pulse from a nearby magnetar would cascade through technological civilization in waves of destruction. Radio telescopes would be permanently damaged by induced currents exceeding their design limits by factors of millions. Communication satellites would experience complete electronics failures within microseconds of the first magnetic field pulse. Even fiber optic communications would be disrupted as the magnetic fields induce currents in metallic components of optical repeaters and switching equipment. The discovery of magnetar precession has revealed these objects as cosmic gyroscopes whose axis of rotation slowly wobbles due to the gravitational torque from their oblate shape. This precession, observed in several magnetars including 1E 1048.1 to 5937, creates periodic modulations in their X-ray emission and provides insights into neutron star interior physics. The precession periods, ranging from months to years, suggest that magnetar crusts are fractured by magnetic stresses to depths approaching the nuclear pasta layers where neutrons begin to drip from atomic nuclei. Yet even magnetars, the most magnetically violent objects known to exist, represent merely another step in the universe's catalog of extremes. Beyond the realm of magnetic field strengths that reshape quantum mechanics itself lie stellar remnants that have crossed different thresholds entirely, where the familiar matter of neutrons gives way to more exotic forms of stellar death. These are the white dwarfs, objects that, paradoxically, might offer the only glimmer of hope for survival in our cosmic replacement scenarios. 5. White dwarfs, the gentlest cosmic corpses. After exploring the cosmic violence of magnetars and the electromagnetic apocalypse they would unleash upon our world, we encounter a stellar remnant that offers something almost unprecedented in our catalog of cosmic horrors: hope. White dwarf stars represent the universe's most gentle form of stellar death, if any word so mild can be applied to objects where a teaspoon of matter weighs as much as an automobile. These Earth-sized remnants of sun-like stars offer the only scenario in our cosmic thought experiment where life might theoretically survive, though the path to that survival requires patience measured in geological epochs and orbital engineering on an astronomical scale. White dwarfs embody the final fate awaiting our own sun, a cosmic preview of Earth's ultimate destiny played out over billions of years. When stars like our sun exhaust their nuclear fuel, they lack the mass necessary to trigger the catastrophic core collapse that births neutron stars or black holes. Instead, they undergo a more gradual death, expanding into red giants that engulf their inner planets before shedding their outer layers into space as planetary nebulae. What remains behind is the star's core, a sphere roughly the size of Earth containing about 60% of the original star's mass, supported against gravitational collapse by electron degeneracy pressure, the quantum mechanical resistance of electrons to being compressed into identical quantum states. The physics governing white dwarf structure reveals matter in a state unknown on Earth yet far more comprehensible than the nuclear density of neutron stars. With typical densities of 10 grams per cubic centimeter, about 1,000,000 times denser than water, white dwarf material exists in a plasma state where atomic nuclei float in a sea of degenerate electrons. The electrons, stripped from their parent atoms by the intense heat and pressure, form a quantum mechanical fluid that provides the pressure necessary to support the star against gravitational collapse. This electron degeneracy pressure operates according to the Pauli exclusion principle, creating a cosmic scale demonstration of quantum mechanics where the wave nature of matter determines the structure of an entire star. Recent discoveries have revolutionized our understanding of white dwarf diversity and behavior. The 2016 confirmation of AR Scorpii as the first white dwarf pulsar shattered previous assumptions about these stellar remnants. Unlike neutron star pulsars that generate lighthouse beams through magnetic field interactions, AR Scorpii creates its pulsar behavior through a complex dynamo mechanism involving interactions between the white dwarf and its red dwarf companion star. The system generates pulses every 1.97 minutes as the white dwarf's magnetic field accelerates electrons to relativistic speeds, creating emissions across the electromagnetic spectrum from radio waves to X-rays. The discovery of a second white dwarf pulsar, J191213.72, 441045. In 2023 to 2024 further expanded our knowledge of these objects' capabilities. This remarkable system spins 300 times faster than Earth's rotation, demonstrating that white dwarfs can maintain rapid rotation despite their compact size and strong magnetic fields. The pulsar mechanism in this system appears to involve magnetic reconnection events that accelerate particles along field lines extending far beyond the white dwarf's surface, creating coherent radio emission through processes still being studied by astronomers worldwide. The mass distribution of white dwarfs spans a narrower range than other stellar remnants, constrained by the Chandrasekhar limit at approximately 1.4 solar masses. Below this threshold, electron degeneracy pressure can indefinitely support the star against gravitational collapse. Above it, the electrons become so compressed that they undergo inverse beta decay, combining with protons to form neutrons and triggering either a type Ia supernova explosion or, in some cases, neutron star formation. This mass limit represents one of the most precise boundaries in astrophysics, determined by fundamental constants of quantum mechanics and relativity. Sirius B, the nearest white dwarf at 8.6 light-years distance, provides an excellent example of these objects' extreme properties. With 0.98 solar masses compressed into a sphere roughly Earth size, it possesses surface gravity approximately 100,000 times stronger than Earth's. An object dropped on Sirius B's surface would accelerate at nearly 10 meters per second squared, reaching speeds of thousands of kilometers per hour in just seconds. The gravitational redshift from this intense gravity field causes light escaping the white dwarf surface to lose about 0.02% of its energy, creating measurable frequency shifts that confirm Einstein's predictions about gravity's effect on electromagnetic radiation. But what would happen if such an object suddenly replaced our Sun? Unlike the immediate catastrophes accompanying black holes, neutron stars, or magnetars, a white dwarf replacement would unfold as a cosmic drama measured in millions of years rather than minutes. The scenario's outcome would depend critically on the white dwarf's age and temperature, factors that determine whether it could provide the gentle, steady energy necessary for life's survival. Young white dwarfs begin their cooling journey at surface temperatures exceeding 100,000 Kelvin, radiating primarily in dangerous ultraviolet wavelengths that would strip away Earth's ozone layer and sterilize the surface through DNA-damaging radiation. However, unlike main-sequence stars that maintain constant luminosity through nuclear fusion, white dwarfs cool predictably as they radiate their stored thermal energy into space. The cooling timeline follows well-understood physics. A white dwarf with initial temperature of 50,000 Kelvin requires approximately 100 million years to cool to 10,000 Kelvin, and another billion years to reach 5,000 Kelvin, roughly the surface temperature necessary for Earth-like habitability. The critical challenge lies in orbital mechanics and the inverse square law of radiation. Earth's current orbital distance of 150 million kilometers would be far too remote to receive adequate heat from a cooling white dwarf. The habitable zone around a white dwarf extends only 0.005 to 0.02 astronomical units from the stellar surface, closer than Mercury's orbit around our current Sunday. At such proximity, Earth would become tidally locked within millions of years, with one hemisphere permanently facing the white dwarf in eternal daylight while the other endures perpetual darkness. The tidal locking scenario would create extreme climate conditions unlike anything in Earth's history. The day side might maintain temperatures suitable for liquid water, while the night side would freeze solid, creating massive atmospheric circulation patterns as gases attempt to redistribute heat between hemispheres. The terminator zone, the boundary between permanent day and night, could potentially harbor a ring of habitable conditions where temperatures remain moderate and liquid water persists. Recent theoretical work has explored the possibility of white dwarf habitability in greater detail. Unlike main-sequence stars that evolve on timescales of billions of years, white dwarfs provide stable energy output for trillions of years as they slowly cool, longer than the current age of the universe. This stability could theoretically support life far longer than any main sequence star, though the initial period of dangerous ultraviolet radiation and the required orbital migration present formidable challenges for any existing biosphere. The visual transformation of our sky under a white dwarf sun would unfold as one of the universe's most gradual spectacles. Initially, the white dwarf would appear as an intensely bright blue-white point of light, much smaller than our current sun but blazingly luminous. Over millions of years, observers would witness a cosmic sunset played out in slow motion as the stellar color shifted from blue to white to yellow to orange to red. Eventually, after billions of years, the white dwarf would fade beyond visible wavelengths while still providing infrared warmth, becoming an invisible heat source detectable only through thermal radiation. The gravitational effects of white dwarf replacement would create measurable but not catastrophic changes to Earth's environment. The intense surface gravity would cause significant gravitational redshift, making spectral lines from the white dwarf appear at longer wavelengths than expected. Time dilation effects, while not extreme, would be measurable. Atomic clocks on Earth would run slightly faster than identical clocks placed on the white dwarf's surface, demonstrating general relativity on a solar system scale. The discovery of white dwarf planets has revealed that planetary systems can indeed survive stellar evolution. The Kepler Space Telescope identified several white dwarfs with orbiting debris disks, and the TRAPPIST-1 system provides a template for how planetary systems might migrate inward as their host stars evolve. Some theoretical models suggest that planets could gradually spiral inward through gravitational interactions as their star transitions to a white dwarf, potentially achieving the close orbits necessary for continued habitability. Perhaps most remarkably, white dwarf archaeology, the study of heavy elements in white dwarf atmospheres, has revealed that many of these stars have consumed rocky planets during their cooling phase. The presence of calcium, iron, and other heavy elements in white dwarf spectra indicates ongoing accretion of planetary material, demonstrating that planetary systems commonly survive stellar evolution and continue to interact with their transformed host stars for billions of years. The magnetic fields of white dwarfs, while much weaker than neutron stars or magnetars, can still reach millions of times Earth's field strength. These fields create unique plasma physics environments where electron-cyclotron radiation generates polarized emissions across multiple wavelengths. The magnetic field geometry, often more complex than simple dipoles, suggests that white dwarf magnetospheres could interact with planetary magnetic fields in ways that might actually enhance habitability by providing additional protection from cosmic radiation. White dwarfs represent our universe's most patient approach to stellar death, objects that offer the possibility of survival through cosmic endurance rather than immediate destruction. Yet even these gentlest of stellar corpses require such dramatic modifications to planetary orbits and atmospheric conditions that survival remains more theoretical possibility than practical reality. Beyond white dwarfs lie even stranger objects that challenge our understanding of matter itself, exotic constructs where the familiar particles of atomic physics give way to theoretical states of matter that exist at the very boundaries of known physics. 6. Exotic objects. Beyond normal matter. While white dwarfs offered a glimmer of hope in our cosmic replacement scenarios, however distant and theoretical that hope might be, we now venture beyond the realm of conventional stellar physics into territories where matter itself abandons the familiar rules of atomic structure. Here, in the universe's most extreme laboratories, theoretical physicists have predicted the existence of objects so strange they challenge our fundamental understanding of what matter can become when pushed beyond every known limit. These are the exotic stars. Quark stars where neutrons dissolve into their constituent particles, boson stars that exist as single macroscopic quantum objects, and hypothetical constructs that blur the boundary between matter and spacetime itself. The journey from conventional stellar remnants to exotic matter begins at the point where even neutron degeneracy pressure, the quantum mechanical force that supports neutron stars, finally succumbs to overwhelming gravitational compression. When matter reaches densities exceeding 10^1 grams per cubic centimeter, roughly 5 times nuclear density, the neutrons themselves may no longer be able to maintain their individual identity. Under such extreme conditions, theoretical models suggest that neutrons could dissolve into their constituent quarks, creating stellar objects composed entirely of free quark matter, a state of matter that may have existed only in the first microseconds after the Big Bang. Quark stars represent the next step beyond neutron stars in the hierarchy of cosmic compression. Where neutron stars contain matter at nuclear density with neutrons packed so tightly they nearly touch, quark stars would consist of a soup of up, down, and potentially strange quarks flowing freely throughout the stellar interior. The transition from neutron matter to quark matter might occur gradually as a mixed phase, or it could happen catastrophically in a phase transition that releases enormous amounts of energy, potentially observable as a special class of gamma-ray bursts or X-ray transients. The theoretical framework for quark stars rests on quantum chromodynamics, the theory describing the strong nuclear force that binds quarks together. At extreme densities, asymptotic freedom allows quarks to move more freely as the strong force paradoxically weakens at short distances. This creates the possibility of stable quark matter that could theoretically exist at lower energies than ordinary nuclear matter, a hypothesis known as the Bodmer-Witten conjecture. If this conjecture proves correct, strange quark matter might represent the true ground state of matter, more stable than the atoms, nuclei, and neutrons from which our familiar world is constructed. Several pulsar candidates have been proposed as possible quark stars based on their unusual observational properties. PSR B0943+10 exhibits cooling rates faster than expected for conventional neutron stars and displays timing irregularities that could result from internal quark matter phase transitions. The neutron star in the supernova remnant 3C58 also cools more rapidly than theoretical models predict for normal neutron star composition, suggesting exotic matter in its core. These observations remain controversial, as alternative explanations involving conventional neutron star physics with modified cooling mechanisms can also account for the observed behaviors. But what cosmic transformation would occur if a quark star suddenly replaced our Sun? The scenario would combine the devastating radiation environment of neutron stars with additional exotic physics unique to free quark matter. A quark star replacement would likely be smaller and denser than a neutron star of equivalent mass, creating even stronger tidal forces at planetary distances. The surface composition might produce unique electromagnetic signatures, potentially visible as unusual spectral lines from quark-antiquark annihilation processes or exotic particle decay chains. The most terrifying possibility involves strange matter conversion, a theoretical process where ordinary matter transforms into strange quark matter upon contact. If strange matter represents the true ground state of matter, any material encountering a strange quark star's surface might undergo conversion, with the transformation front potentially spreading at significant fractions of light speed. This process could theoretically convert entire planets or even stars into strange matter, representing a universe-altering catastrophe that would make black hole formation seem gentle by comparison. Moving beyond quark stars, we encounter boson stars, purely theoretical constructs that exist as gravitationally bound quantum condensates on astronomical scales. Unlike any conventional star powered by nuclear fusion or supported by degeneracy pressure, boson stars would consist entirely of bosonic particles held together by their own gravity while maintaining coherent quantum mechanical properties across stellar dimensions. These objects would behave as single, massive quantum entities, macroscopic realizations of phenomena typically confined to atomic and subatomic scales. The most studied variety of boson stars consists of hypothetical axion particles, ultralight bosons with masses around 10 superscript 2 superscript 2 electron volts that could form gravitationally bound states through Bose-Einstein condensation on cosmic scales. Axion stars would form through gravitational collapse of axion dark matter over densities, with formation timescales ranging from 10 million to 1 billion years, depending on the initial density distribution and axion self-interaction strength. The resulting objects could range in mass from asteroid-scale microboson stars to objects rivaling neutron stars in total mass. Recent gravitational wave observations have sparked speculation about boson star detectability. The 2020 detection of GW 190521 by LIGO Virgo revealed merging objects with masses falling within the theoretical mass gap, where stellar black holes shouldn't exist according to conventional stellar evolution models. Some researchers propose that the merging objects might have been boson stars rather than black holes, though this interpretation remains highly controversial and requires exotic boson properties not predicted by current particle physics theories. A boson star replacement for our Sun would create the most ethereal form of cosmic destruction. These objects produce minimal electromagnetic radiation, appearing as gravitational mirages that bend light from background stars while remaining largely invisible themselves. The lack of surface features, emission lines, or thermal radiation would create an eerie dark lens effect, with stars appearing and disappearing as gravitational focusing changes their apparent positions. The sky would become a constantly shifting pattern of distorted and magnified stellar images surrounding an invisible gravitational phantom. The gravitational effects would depend entirely on the boson star's mass and internal structure. If the mass equaled our Sun's, planetary orbits might remain stable, but the internal quantum structure could create unique signatures in gravitational wave production or exotic particle interactions with planetary magnetic fields. Quantum effects operating on astronomical scales might produce phenomena unknown in conventional astrophysics. The entire boson star could act as a single quantum object, potentially exhibiting macroscopic quantum interference effects or sudden quantum transitions between energy states. The stability of boson stars depends critically on the self-interaction properties of their constituent particles. Without self-interactions, boson stars would be unstable to small perturbations, eventually dispersing into non-gravitationally bound particle clouds. However, attractive self-interactions could stabilize these objects, while repulsive interactions might create oscillating boson stars that periodically expand and contract on timescales determined by the particle mass and interaction strength. Beyond boson stars lie even more speculative exotic objects that push theoretical physics to its absolute limits. Q-stars, composed of hypothetical Q-balls, stable, non-topological solitons predicted by supersymmetric theories, could theoretically outmass ordinary stars while maintaining stability through exotic field configurations. These objects would represent macroscopic manifestations of particle physics beyond the standard model, potentially detectable through gravitational lensing effects or exotic radiation signatures. Prion stars represent another theoretical possibility, composed of hypothetical particles more fundamental than quarks and leptons. If prions exist as constituents of known particles, they might form stable bound states under extreme gravitational compression, creating objects even denser than quark stars. The physics governing prion stars remains purely speculative, as no evidence for prion substructure has been observed in high-energy particle experiments. The recent theoretical work on asymptotically safe quantum gravity has suggested new possibilities for exotic stellar objects. Manuel Reichert and Yuri Smirnov's 2025 research constrains scalar dark matter particle masses to 56 to 63 GeV ranges and fermionic dark matter below 50 TeV, providing boundary conditions for dark matter stars, hypothetical objects composed entirely of dark matter particles held together by gravity and potentially their own self-interactions. Dark matter stars could theoretically exist as invisible stellar objects detectable only through gravitational effects. If dark matter particles possess significant self-interaction cross-sections, they could form stable, long-lived objects that would appear as invisible gravitational lenses causing unexplained stellar motions and gravitational lensing events. The replacement of our Sun with a dark matter star would create the ultimate invisible catastrophe. Earth would continue orbiting normally while receiving no energy whatsoever, leading to immediate climate collapse and atmospheric freezing. The study of exotic stellar objects reveals the universe's capacity for creating matter configurations that challenge every assumption about the nature of reality itself. From quark soups that dissolve the boundaries between particles to quantum condensates that maintain coherence across stellar scales, these theoretical objects demonstrate that our universe operates according to physical laws far stranger than everyday experience suggests. Yet, even these exotic constructs pale in comparison to the ultimate theoretical possibility in our cosmic replacement scenarios. Beyond objects composed of strange matter, quantum fields, or dark particles lies the most mind-bending concept in all of theoretical physics: wormholes that could connect our solar system to distant regions of spacetime, creating windows through the fabric of reality itself that would transform our understanding of space, time, and causality in ways that challenge the very foundations of physical law. 7. Wormholes, tunnels through space-time. From the exotic matter configurations that challenge our understanding of particles and fields, we now arrive at the most audacious possibility in our cosmic thought experiment: objects that transcend matter entirely to become pure geometry made manifest. Wormholes represent solutions to Einstein's field equations so mathematically elegant yet physically impossible that they blur the boundary between theoretical physics and science fiction. These hypothetical tunnels through spacetime could, in principle, connect our solar system to distant regions of the universe, different cosmic epochs, or even parallel realities, transforming our sun's replacement from an exercise in stellar physics into a gateway that would redefine the very meaning of existence itself. The mathematical foundation for wormholes emerged from Einstein and Nathan Rosen's 1935 analysis of black hole solutions to general relativity. They discovered that the equations permitted bridges connecting separate regions of spacetime through higher dimensional shortcuts that bypass the normal 3 dimensions of space. These Einstein-Rosen bridges represent pure geometric constructs where spacetime curves so severely that it effectively folds back upon itself, creating tunnels that could theoretically allow instantaneous travel across cosmic distances that would require millions or billions of years to traverse through normal space. The physics governing wormhole stability presents challenges that push theoretical understanding to its absolute limits. For a wormhole to remain open and traversable, it must possess what physicists call a flared throat, a region where the tunnel widens rather than contracts, preventing gravitational collapse that would pinch off the connection and trap anything attempting to pass through. Maintaining this geometry requires exotic matter with negative energy density, a theoretical substance that violates the null energy condition of general relativity and may not exist anywhere in the observable universe. Recent theoretical breakthroughs have explored quantum mechanical mechanisms that might stabilize traversable wormholes without exotic matter. Daniel Jeffries and his colleagues at Harvard University demonstrated that quantum entanglement between the mouths of a wormhole could theoretically provide the negative energy necessary to keep the tunnel open. This work builds on the holographic principle and adds/CFT correspondence, suggesting that quantum entanglement and spacetime geometry might be fundamentally connected at the deepest levels of physical reality. The 2022 quantum computer simulation conducted by Maria Spiropoulou's team at Caltech provided the first experimental glimpse into wormhole dynamics, using Google's Sycamore processor to simulate a simplified model based on the Suchdev-Yekitarev (SYK) quantum mechanical system. While critics argued that the simulation was too simplified to capture true gravitational physics, the experiment demonstrated information teleportation through quantum entangled systems in ways that mirror theoretical predictions for wormhole behavior. The simulation showed how quantum information could traverse from one side of the wormhole to the other, providing experimental validation of the deep connections between quantum mechanics and space-time geometry. But what unimaginable scenario would unfold if an actual traversable wormhole suddenly replaced our sun? The replacement would create the most exotic gravitational environment possible, where the normal relationship between space and time dissolves into a cosmic hall of mirrors. The extreme spacetime curvature around the wormhole throat would produce gravitational lensing effects far more dramatic than any conventional massive object, creating multiple images of background stars and severe distortions of the stellar field that would transform the night sky into an ever-shifting kaleidoscope of light. The visual appearance would be unprecedented in human experience. Looking toward the wormhole, observers on Earth might see distorted images of a completely different region of the universe appearing around the dark throat opening. Stars, galaxies, or even cosmic structures from different epochs could become visible, creating a window to distant spacetime that would revolutionize astronomy overnight. The relativistic effects would create time delays and frequency shifts in light arriving from the far side, potentially allowing observations of the wormhole's destination in slow motion or time-lapse, depending on the relative motion and gravitational fields of the connected regions. The gravitational effects would depend critically on the wormhole's total mass energy and internal geometry. If the exotic matter configuration possessed mass equivalent to our Sun, planetary orbits might remain stable, though the internal structure would create unique signatures unlike any conventional massive object. Tidal forces might exhibit unusual directional changes as objects approach the throat region, following geodesics through curved spacetime that could accelerate matter in directions impossible under Newtonian gravity. The throat region itself would represent a zone where the normal relationship between space and time breaks down completely. Objects approaching the wormhole mouth would experience extreme gravitational lensing, seeing multiple distorted images of the surrounding universe as light follows curved paths through the warped spacetime geometry. The throat might appear as a dark region surrounded by highly magnified and distorted images of whatever lies on the wormhole's far side, potentially revealing cosmic structures billions of light-years away or even glimpses of different cosmic epochs if the wormhole connected regions with different gravitational time dilation. Traversing through a wormhole would create the ultimate relativistic experience. The journey through the throat might subjectively take only minutes or hours from the traveler's perspective, while external observers could see the process unfold over completely different timescales depending on the gravitational fields involved. The extreme curvature near the throat would create tidal effects, though these might be survivable if the wormhole were sufficiently large. Objects with throats measured in astronomical units rather than kilometers could theoretically allow passage without spaghettification. The exotic matter requirements for wormhole stability involve physics that operates at the intersection of quantum field theory and general relativity. The Casimir effect, which creates negative energy density between parallel conducting plates through quantum vacuum fluctuations, demonstrates that negative energy can exist on microscopic scales. However, scaling these effects to the enormous energies required for macroscopic wormholes presents challenges that may prove physically impossible. The total negative energy required could exceed the mass energy of entire stars, requiring control over quantum fields on scales far beyond current technological capabilities. Recent advances in holographic duality and the ADS/CFT correspondence have suggested new approaches to wormhole physics. The ER equals EPR conjecture, proposed by Leonard Susskind and Juan Meldacena, suggests that quantum entanglement and wormhole geometry might be fundamentally the same phenomenon viewed from different perspectives. This could mean that sufficiently complex quantum entangled systems might naturally create the space-time geometry of traversable wormholes, though the energy requirements and control mechanisms remain far beyond current understanding. The concept of microscopic wormholes has emerged from quantum gravity theories, where virtual wormholes might spontaneously form and decay at the Planck scale, distances of approximately 10^3 meters where quantum effects become important for gravitational physics. These quantum wormholes could theoretically be artificially expanded through unknown mechanisms involving exotic matter or advanced manipulation of quantum fields, though such technology would require mastery over fundamental forces at levels that may be forever beyond reach. Wormhole networks represent the ultimate expression of advanced cosmic engineering, where civilizations might theoretically connect distant regions of the galaxy or universe through artificially created space-time tunnels. Such networks could enable instantaneous communication and travel across cosmic distances, fundamentally altering the nature of space exploration and interstellar civilization. However, the stability requirements for such networks would demand continuous input of exotic matter and careful management of gravitational fields to prevent catastrophic collapse. The possibility of naturally occurring wormholes in our universe remains one of the greatest open questions in theoretical physics. Primordial wormholes could theoretically have formed during cosmic inflation in the early universe, when quantum fluctuations in spacetime geometry might have created stable tunnel configurations. These ancient wormholes could still exist today, though detecting them would require observational signatures that might be impossible to distinguish from other exotic objects like primordial black holes or dark matter concentrations. The replacement of our Sun with a traversable wormhole would transform Earth from a planetary observatory into a cosmic portal, fundamentally altering humanity's relationship with the universe itself. The ability to observe distant cosmic regions directly through the wormhole throat would accelerate astronomical discovery by millions of years, providing immediate access to information that would otherwise require interstellar travel or billion-year observation campaigns. Yet, the stability challenges for such an object would create constant existential anxiety for any surviving civilization. Wormholes exist at the knife's edge of gravitational collapse, requiring precise control over exotic matter distributions and quantum field configurations to prevent catastrophic closure. Any disruption to the delicate balance maintaining the tunnel could result in instant collapse, potentially trapping anything within the throat region and converting the entire structure into a conventional black hole. The electromagnetic environment around wormholes remains largely unexplored in theoretical physics, though the intense spacetime curvature would likely create unique plasma physics phenomena. Charged particles following geodesics through the curved spacetime might generate electromagnetic radiation patterns unlike anything produced by conventional astrophysical objects, potentially creating observable signatures that could distinguish wormholes from other exotic objects. Perhaps most remarkably, wormholes represent the ultimate convergence of theoretical physics, where general relativity, quantum mechanics, and exotic matter physics combine to create objects that exist at the very edge of physical possibility. They embody the universe's capacity for geometric configurations so extreme they challenge our fundamental concepts of space, time, and causality, representing not merely objects that could replace our Sun, but gateways that could transform our understanding of reality itself into something utterly unrecognizable. As we prepare to examine how recent astronomical discoveries have transformed these theoretical speculations into quantitatively precise predictions, the wormhole scenario stands as the ultimate reminder that our universe operates according to physical laws far stranger and more wonderful than everyday experience suggests. Laws that permit not only the existence of objects that bend light and warp time, but potentially even tunnels through the fabric of reality itself. Recent discoveries. The revolution in understanding. From the realm of pure theoretical speculation, where wormholes exist as elegant mathematical solutions dancing on the edge of physical impossibility, we emerge into an era of unprecedented observational triumph that has transformed cosmic mysteries into quantitatively precise science. The past 5 years have witnessed a revolution in astronomy, so profound that objects once relegated to the theoretical imagination now reveal their secrets through direct observation, gravitational wave detection, and electromagnetic imaging. These discoveries have converted our cosmic replacement scenarios from exercises in speculative physics into carefully calibrated predictions of destruction, survival, and the fundamental limits of reality itself. The transformation began with humanity's first direct detection of gravitational waves, ripples in the fabric of spacetime itself that Einstein predicted but never expected we would observe. When LIGO detected GW 150914 on September 14, 2015, astronomers witnessed two black holes spiraling into each other 1.3 billion years ago, their final cosmic dance releasing more energy in gravitational waves than all the stars in the observable universe emit in light. But this historic first detection represented merely the opening note of a symphony of cosmic violence that would fundamentally reshape our understanding of the universe's most extreme objects. The LIGO-Virgo-Cagra collaboration achieved a stunning milestone in March 2025 with their announcement of the 200th gravitational wave detection during the O4 observing run. These detections now occur at an extraordinary rate of one cosmic merger every 2 to 3 days, revealing a universe filled with colliding black holes and neutron stars far more numerous and active than theoretical models had predicted. The detection sensitivity has expanded dramatically since the early observations. Binary neutron star mergers can now be observed up to 550 million light-years away, compared to 250 million light-years during the first observing run, while black hole mergers are detectable across distances exceeding 8 billion light-years. Each gravitational wave detection provides exquisitely precise measurements of mass, spin, and orbital dynamics that would be impossible to obtain through electromagnetic observations alone. The chirp mass, a combination of the individual masses that determines the gravitational wave frequency evolution, can be measured to fractional uncertainties of less than 1%, while the final black hole spin can be constrained to within a few percent. These measurements have revealed black hole populations with properties that challenge theoretical formation models, including unexpectedly massive stellar black holes and spin distributions that suggest complex evolutionary histories. The discovery of mass gap objects has particularly intrigued astronomers studying extreme stellar evolution. GW 230529, detected in May 2023, involved a mysterious compact object between 2.5 and 4.5 solar masses, a range where neither neutron stars nor black holes were expected to exist according to conventional stellar evolution theory. This detection suggests either new formation mechanisms for compact objects or exotic matter states that bridge the gap between stellar remnants, potentially including quark stars or other exotic configurations that exist at the boundaries between neutron star and black hole physics. The most massive gravitational wave source detected to date, GW 190521, created a 142 solar mass intermediate black hole through the merger of 85 and 66 solar mass progenitors. The event released energy equivalent to 8 solar masses in gravitational waves over a duration of less than 0.1 seconds, demonstrating the universe's capacity for energy release on scales that dwarf stellar explosions. The progenitor masses fell within theoretical gaps where stellar black holes shouldn't exist, suggesting either exotic formation mechanisms or evolution through multiple merger generations in dense stellar environments. Simultaneously, the Event Horizon Telescope achieved what many considered impossible: direct imaging of the event horizon shadows cast by supermassive black holes. The April 2019 image of M87** revealed the first visual confirmation of an event horizon, showing a dark circular shadow surrounded by a bright accretion disk exactly as Einstein's general relativity predicted. The image resolved features just 40 microarcseconds across, equivalent to reading a newspaper on the Moon from Earth, through a planet-spanning array of radio telescopes operating in perfect synchronization. The May 2022 revelation of Sagittarius A**'S image brought this technology closer to home, capturing our galaxy's central black hole despite observational challenges created by its rapid variability and the intervening interstellar medium. The images revealed organized magnetic field structures remarkably similar between M87* and Sagittarius A** despite their billion-fold mass difference, suggesting universal properties in black hole accretion physics that operate across the entire range of supermassive black hole masses. These direct observations have confirmed theoretical predictions about black hole environments with stunning precision. The magnetic field strengths inferred from polarized light observations reach 10,000 times Earth's magnetic field, providing the energy source for relativistic jets that extend thousands of light-years from the black hole. The rotation measurements show both M87* and Sagittarius A** spinning at significant fractions of their maximum possible rates, confirming that these objects store enormous amounts of rotational energy that powers some of the most energetic phenomena in the universe. The James Webb Space Telescope has revolutionized neutron star astronomy through infrared observations that penetrate dust and reveal stellar remnants invisible to optical telescopes. The historic July 2024 detection of neutron star emission from supernova remnant SN 1987A ended a 37-year search that began when the supernova was first observed in 1987. Webb detected highly ionized argon and energetic photons characteristic of neutron star surface emission, confirming theoretical models of stellar collapse and providing the first direct evidence of neutron star birth from stellar explosion. The infrared capabilities have also revealed the aftermath of neutron star mergers with unprecedented detail. Webb's observations of kilonova GRB 230307A provided the first direct detection of tellurium, a heavy element created through rapid neutron capture processes during neutron star collisions. The merger occurred 120,000 light-years from its host galaxy, demonstrating the violent kicks that neutron stars receive during formation and the vast distances over which these cosmic element factories can operate. Multi-messenger astronomy has emerged as the new paradigm for studying extreme cosmic events, combining gravitational waves, electromagnetic radiation, and particle detections to provide comprehensive views of cosmic catastrophes. The August 2017 detection of GW 170817 inaugurated this field by simultaneously observing gravitational waves from merging neutron stars and the electromagnetic fireworks that followed, including gamma-ray bursts, optical kilonovae, and radio afterglows that persisted for months after the initial collision. These combined observations have revealed neutron star mergers as cosmic element factories responsible for creating gold, platinum, and other elements heavier than iron. The total mass of heavy elements produced in a single merger can exceed Earth's entire mass, distributing these materials across galactic distances through explosive outflows traveling at significant fractions of light speed. The discovery has solved the long-standing mystery of heavy element origins while demonstrating the crucial role that stellar death plays in cosmic chemical evolution. Fast radio bursts have emerged as another window into extreme astrophysics, with the April 2020 detection of FRB 200428 from magnetar SGR 1935 plus 2154, providing the first confirmed link between these mysterious millisecond duration flashes and magnetar activity. The burst released more energy in radio waves than our Sun emits across all wavelengths in several days, demonstrating that magnetars can generate radio emissions billions of times brighter than typical pulsar signals through magnetic reconnection events that accelerate particles to extreme energies. The statistical analysis of gravitational wave populations has revealed unexpected diversity in compact object properties that inform our replacement scenarios. Black hole spins show a bimodal distribution suggesting two distinct formation channels, while neutron star masses cluster near 1.4 solar masses with a tail extending toward the maximum mass limit. The merger rate measurements indicate that cosmic collisions occur far more frequently than expected, with binary neutron star mergers happening roughly once every 100,000 years within a sphere of 200 million light-years around Earth. Advanced computer simulations have reached unprecedented sophistication in modeling these extreme scenarios. Numerical relativity calculations can now follow black hole mergers from initial and spiral through final ring down with accuracy sufficient to match LIGO observations to within measurement uncertainty. Magnetohydrodynamic simulations of neutron star mergers reveal the complex interplay between magnetic fields, plasma dynamics, and relativistic flows that power electromagnetic counterparts to gravitational wave events. The implications for our cosmic replacement scenarios are profound. We now possess precise measurements of how black holes, neutron stars, and exotic objects behave under extreme conditions, allowing quantitative predictions of their effects on planetary systems. The gravitational wave observations provide exact masses and spins. Electromagnetic imaging reveals magnetic field strengths and plasma properties, and multi-messenger detections show how these objects interact with their environments across cosmic distances. The discovery that massive stellar black holes exist well above previous theoretical limits suggests that our Sun could potentially be replaced by black holes more massive than previously thought possible. The observation of magnetar behavior through fast radio bursts reveals electromagnetic environments even more extreme than theoretical models predicted. The direct imaging of accretion disks shows plasma configurations that would create visual spectacles and radiation environments more complex and dangerous than earlier calculations suggested. Perhaps most remarkably, these observations have revealed that the universe produces extreme objects with far greater frequency and diversity than theoretical models predicted. The cosmic merger rate measured through gravitational waves exceeds predictions by factors of several, suggesting that the universe's capacity for creating and destroying extreme matter configurations operates on scales that challenge our understanding of stellar evolution and cosmic structure formation. These discoveries transform our cosmic thought experiment from speculative fiction into precise physics, where the mathematics of destruction and survival can be calculated with the same accuracy used to predict planetary orbits or stellar evolution. The universe has revealed itself as both more violent and more creative than we imagined, producing objects that push physics to its absolute limits while operating according to mathematical laws precise enough to predict their behavior across cosmic time and distance scales. As we prepare to explore the visual spectacles and electromagnetic chaos that would accompany these cosmic replacements, we do so armed with observational data that converts imagination into calculation, theory into measurement, and speculation into the precise mathematics of cosmic catastrophe made real. 9. The visual spectacle, what we would see. Armed with unprecedented observational data from gravitational wave detectors, space telescopes, and direct imaging of cosmic extremes, we can now paint precise pictures of humanity's final moments under alien skies. The recent revolution in astronomy has transformed abstract theoretical predictions into vivid, calculable realities. We know exactly what the heavens would look like as our familiar sun gives way to objects that bend light itself, create aurora displays spanning entire hemispheres, and generate electromagnetic phenomena that exist nowhere else in the cosmos. These would be the last spectacles witnessed by human eyes, cosmic light shows of such impossible beauty and terror that they would redefine forever our understanding of what the universe can create when physics operates without restraint. The transformation would begin with the most subtle yet profound change imaginable, the gradual realization that something fundamental about light itself had been altered. If our sun vanished instantaneously, replaced by any of these cosmic monsters, the first 8 minutes and 20 seconds would unfold in deceptive normalcy as the last photons from our departed star completed their 93 million-mile journey to Earth. Sunrise would occur exactly on schedule, shadows would fall in familiar patterns, and the golden light that has illuminated human civilization for millennia would continue to warm our world with no indication of the cosmic catastrophe that had already sealed our fate. Then, at precisely 8 minutes and 20 seconds after replacement, darkness would fall with the abruptness of a cosmic switch being thrown. But this would not be the gentle darkness of nightfall or even the temporary shadow of a solar eclipse. This would be the absolute darkness of a world severed from its energy source, broken sunlight patterns giving way to alien illumination that would announce the arrival of objects whose very existence challenges the comfortable physics of our everyday experience. The visual spectacle accompanying black hole replacement would unfold as perhaps the most subtle yet psychologically devastating cosmic transformation imaginable. Initially, the replacement object would remain completely invisible, a perfectly black sphere occupying the position where our sun once shone, detectable only through its gravitational effects on the motion of planets and the bending of starlight around its event horizon. The night sky would become a surreal gallery of distorted stellar images as gravitational lensing curved the paths of photons from distant stars, creating multiple images of single objects and Einstein rings, perfect circles of light surrounding the invisible gravitational lens. If the black hole acquired an accretion disk from solar wind material, cometary debris, or disrupted asteroids, the visual transformation would accelerate into one of the universe's most spectacular and deadly phenomena. Matter spiraling into the black hole would heat to temperatures exceeding 10 million Kelvin through gravitational compression and magnetic field interactions, creating a brilliant disk of plasma that could outshine our original sundae. The relativistic Doppler effect would make one side of the disk appear much brighter than the other as matter approaches light speed, creating an asymmetric cosmic whirlpool of light surrounding the dark event horizon shadow. The Event Horizon Telescope's images of M87* and Sagittarius A* provide exact templates for what such a spectacle would look like. The black hole shadow would appear as a dark circle approximately 2.6 times the Schwarzschild radius, surrounded by a bright photon ring where light orbits the black hole multiple times before escaping. The magnetic field structures revealed in these observations suggest that relativistic jets, narrow beams of particles and energy extending thousands of times the black hole's diameter, could form if sufficient material feeds the accretion process. Neutron star replacement would create the most violently stroboscopic sky imaginable, transforming day and night into concepts measured in milliseconds rather than hours. The most rapidly spinning pulsar, PSR J1748-2446 AD, completes 716 rotations per second, creating lighthouse beams that would sweep across Earth faster than human perception can follow. Each pulse would deliver concentrated bursts of X-ray radiation lethal to all surface life, while the intervals between pulses would reveal a pinpoint of blue-white light far more brilliant than our Sun, yet occupying barely a thousandth of its apparent size. The James Webb Space Telescope's detection of neutron star emission from SN 1987A revealed surface temperatures exceeding 1 million Kelvin and magnetic field-driven plasma phenomena that would create aurora displays spanning Earth's entire atmosphere. The neutron star's magnetic field, up to 1 trillion times stronger than Earth's, would interact catastrophically with our planet's magnetosphere, accelerating charged particles to relativistic speeds and generating electromagnetic radiation across the entire spectrum from radio waves to gamma rays. Magnetar replacement would produce the most chaotic and beautiful cosmic light show ever witnessed, surpassing even the neutron star scenario in sheer electromagnetic violence. The quadrillion-strength magnetic fields would create massive coronal loops of plasma arching millions of kilometers into space, guided by field line geometries more complex than any terrestrial aurora. These structures would dwarf anything in our solar system, with individual magnetic flux tubes carrying more energy than the total output of human civilization. The discovery of Swift J 1818.0-1607 and other young magnetars has revealed that these objects can maintain rapid rotation while generating the most powerful magnetic fields in the universe. The resulting starquakes would periodically reconfigure the entire magnetic architecture, creating sudden brightness changes and spectacular reorganizations of the plasma loops that would be visible as dramatic reconfigurations of the sky itself. Each starquake would release gamma-ray bursts equivalent to our Sun's total energy output over thousands of years, creating brief moments when the magnetar outshines every other object in the sky. The electromagnetic chaos would extend far beyond visible light into radio frequencies that would overwhelm all human communications. The April 2020 detection of a fast radio burst from magnetar SGR 1935 plus 2154 demonstrated that these objects can generate radio emissions billions of times brighter than typical pulsars, creating electromagnetic interference that would make electronic communication impossible across the entire planet. The radio sky would become a cacophony of signals so intense they could damage unshielded electronics through induced currents. White dwarf replacement would offer the gentlest visual transformation, though one that would unfold over cosmic timescales that dwarf human civilization. A young white dwarf would initially appear as an intensely bright blue-white point of light, much smaller than our current sun but blazingly luminous. The discovery of white dwarf pulsars like AR Scorpii has revealed that some of these objects can generate lighthouse-like emissions through dynamo mechanisms, creating regular pulses every few minutes rather than the millisecond flashes of neutron star pulsars. Over millions of years, observers would witness a cosmic sunset played out in extreme slow motion as the white dwarf color shifted from blue to white to yellow to orange to red. The cooling timeline follows well-understood stellar physics. A white dwarf with initial temperature of 50,000 Kelvin requires approximately 100 million years to cool to 10,000 Kelvin, and another billion years to reach the 5,000 Kelvin necessary for Earth-like habitability. Eventually, after billions of years, the white dwarf would fade beyond visible wavelengths while still providing infrared warmth, becoming an invisible heat source detectable only through thermal radiation. The gravitational effects would create measurable visual distortions even around white dwarfs. The intense surface gravity causes significant gravitational redshift, making spectral lines appear at longer wavelengths than expected from conventional stars. Time dilation effects would be subtle but detectable. Light escaping the white dwarf's gravitational well would lose approximately 0.02% of its energy, creating frequency shifts visible in high-resolution spectroscopy. Exotic object replacements would create visual phenomena that transcend normal physics entirely. Quark stars might produce unique electromagnetic signatures from quark-antiquark annihilation processes, creating spectral lines that exist nowhere else in the universe. The theoretical possibility of strange matter conversion would add psychological terror to the visual experience. Any material that came into contact with the star's surface might undergo transformation into strange matter, with visible conversion fronts potentially spreading across planetary surfaces at significant fractions of light speed. Boson star replacement would create the most ethereal cosmic phantom imaginable. These objects produce minimal electromagnetic radiation, appearing as invisible gravitational lenses that bend light from background stars, while remaining essentially invisible themselves. The night sky would become a constantly shifting pattern of distorted and magnified stellar images, with stars appearing to dance in impossible patterns as their light follows curved paths through the boson star's gravitational field. Wormhole replacement would transform the sky into a cosmic window to distant regions of spacetime. Looking toward the wormhole throat, observers might see distorted images of completely different cosmic environments, distant galaxies, alien star fields, or even cosmic structures from different epochs if the wormhole connected regions with different gravitational time dilation. The extreme spacetime curvature would create multiple images of background objects, with some stars appearing to orbit around the wormhole mouth as their light follows complex geodesics through the warped geometry. The final visual element in all scenarios except white dwarfs would be the gradual atmospheric collapse as Earth's climate system shuts down without solar energy input. Within weeks, carbon dioxide would begin condensing into dry ice at the poles, creating visible atmospheric changes as the greenhouse effect collapses. The aurora phenomena generated by exotic object interactions with Earth's magnetosphere would gradually fade as our planet's magnetic field weakens without the solar wind interactions that help maintain it. Perhaps most poignantly, the familiar constellations would remain unchanged throughout these cosmic transformations. Orion, the Big Dipper, and the Southern Cross would continue their eternal dance across the sky, providing final comfort to any surviving observers as the cosmos demonstrates its capacity for creating beauty and terror on scales that render human experience insignificant. These would be humanity's last glimpses of the universe that created us. Alien skies illuminated by physics pushed beyond every limit, revealing the true power and strange beauty that emerge when reality itself becomes unrecognizable. The precision with which modern astronomy can predict these visual spectacles represents perhaps the most remarkable achievement in the history of human science. The ability to calculate exactly what impossible things would look like when the universe abandons its gentle treatment of our small corner of spacetime. 10. Survival scenarios. Life in impossible conditions. As the alien skies fade from their final impossible displays and the last photons of our departed sun complete their journey across a solar system transformed beyond recognition, a more haunting question emerges from the cosmic darkness. Could anything, anywhere, survive the replacement of our life-giving star with objects that represent the universe's most extreme expressions of physics? The answer reveals life's most profound secret, not its fragility in the face of cosmic violence, but its stubborn, almost incomprehensible tenacity in environments so hostile they seem designed by malevolent gods to extinguish every spark of biological activity. The mathematics of survival begin with energy, the fundamental currency that powers every biological process from the firing of neurons to the reproduction of the simplest bacteria. Our sun floods Earth with 1.74 times 10 superscript 1 watts of power, energy that drives photosynthesis, weather systems, ocean currents, and ultimately every food chain that has ever existed on our planet. When that energy source vanishes, whether replaced by the invisible hunger of black holes, the lethal radiation of neutron stars, or the electromagnetic chaos of magnetars, life must either find alternative energy sources or face extinction measured not in geological epochs but in hours, days, or at most years. Yet hidden beneath our feet lies a parallel biosphere that has never depended on sunlight, an alien ecology that thrives in conditions so extreme they mirror the environments we might expect on worlds orbiting the very cosmic monsters we've examined. Deep subsurface ecosystems exist throughout Earth's crust, extending down to depths of several kilometers, where temperatures approach the boiling point of water and pressures crush normal cellular structures. These communities derive energy from chemosynthesis, the biochemical process that extracts energy from chemical reactions involving hydrogen sulfide, methane, iron compounds, and other substances that exist independent of solar radiation. The discovery of life around hydrothermal vents has revealed ecosystems that operate according to entirely different biological principles than surface life. Tube worms reaching 2 meters in length harbor symbiotic bacteria that convert hydrogen sulfide into organic compounds, creating food chains that begin with chemistry rather than photosynthesis. Hyperthermophilic archaea thrive at temperatures exceeding 120 degrees Celsius, while extremophilic bacteria have been found living in rock formations over 3 kilometers beneath the surface, sustained by the radioactive decay of uranium, thorium, and potassium in the surrounding geology. Earth's radioactive decay provides approximately 4.4 times 10 superscript 1 superscript 3 watts of geothermal energy, less than 0.03% of solar input, but sufficient to maintain liquid water in localized underground environments for millions of years after surface temperatures plummet to near absolute zero. This energy source operates independently of any external star, powered by isotopes created in supernovae billions of years ago and locked within our planet's interior since its formation. Unlike solar energy, which varies with weather, seasons, and atmospheric conditions, geothermal energy provides steady, reliable power that will continue for billions of years as Earth's radioactive elements undergo their inevitable decay. The black hole replacement scenario, paradoxically, offers the longest potential survival timeline among our cosmic catastrophes. Without the immediate sterilization from high-energy radiation that accompanies neutron stars or magnetars, deep subsurface life could theoretically persist using geothermal energy sources for millions of years. Surface temperatures would plummet to approximately minus 270 degrees Celsius within weeks as the atmosphere freezes and condenses, but underground environments could maintain temperatures above freezing through geothermal heating for geological periods. The survival timeline would unfold with mathematical precision. Photosynthesis would cease within hours as chlorophyll molecules exhausted their stored light energy, triggering immediate collapse of all surface food chains dependent on plant life. Ocean temperatures would begin dropping within days, though the thermal mass of water would delay complete freezing for months or even years in deep ocean basins. Atmospheric collapse would accelerate as carbon dioxide condensed into dry ice within weeks, followed by nitrogen and oxygen liquefaction, leaving only a thin residual atmosphere of noble gases that would eventually freeze solid. Yet in the deepest ocean trenches, around mid-ocean ridges, and in underground aquifers heated by radioactive decay, liquid water could persist indefinitely. These environments already harbor complex ecosystems that have evolved to thrive without sunlight, demonstrating that life can adapt to energy sources far more exotic than the familiar fusion reactions of main-sequence stars. Methanogenic archaea can extract energy from simple organic compounds, sulfur-reducing bacteria can metabolize sulfate compounds, and iron-oxidizing bacteria can derive energy from redox reactions involving metallic minerals. The technological challenges for human survival would prove far more daunting than the biological ones. Modern civilization depends critically on electronic systems that would be instantly destroyed by the electromagnetic environments surrounding neutron stars, magnetars, or active black holes with accretion disks. The electromagnetic pulse from a magnetar would generate induced currents millions of times stronger than nuclear weapons, permanently disabling all semiconductor-based technology and reducing human society to pre-industrial conditions within seconds. Power generation would become the critical limiting factor for any human survival attempt. Nuclear reactors could theoretically continue operating using uranium or thorium fuel, though the loss of electronic control systems would require manual operation under conditions where radiation shielding becomes even more critical without electronic monitoring systems. Geothermal power plants could continue generating electricity using steam from underground heat sources, though maintaining such systems without computerized controls and electronic sensors would prove extremely challenging. Underground survival habitats would need to address fundamental life support challenges without the global systems that currently sustain human civilization. Oxygen production would require either stored chemical supplies or biological systems capable of photosynthesis using artificial light sources. Water recycling would become critical as the global water cycle shuts down without solar energy to drive evaporation and precipitation. Food production would depend entirely on hydroponics, stored supplies, or cultivation of chemosynthetic organisms that could derive energy from available chemical sources. The neutron star and magnetar scenarios offer virtually no survival possibilities for complex life. The X-ray flux from neutron stars would deliver radiation doses of 10 superscript 1 superscript 2 gray per second at Earth's orbital distance, instantly lethal levels that would destroy molecular bonds in living tissue and sterilize the planet at the cellular level. Even brief exposure measured in microseconds would prove fatal, while longer exposures would break down atomic nuclei and eliminate any possibility of biological chemistry. The magnetic field effects would prove equally devastating for any technological survival attempts. Magnetar magnetic fields quadrillion times stronger than Earth's would induce electrical currents capable of melting metallic structures and generating temperatures hot enough to ignite combustible materials through electromagnetic induction alone. Even radiation-hardened electronics designed for space applications would be destroyed within microseconds of exposure to such field strengths. White dwarf replacement scenarios present unique challenges that combine immediate danger with long-term possibilities. Young white dwarfs emit primarily in dangerous ultraviolet wavelengths that would strip away Earth's ozone layer within days, allowing lethal solar ultraviolet radiation to reach the surface. However, the gradual cooling of white dwarfs over millions of years creates the theoretical possibility of eventual habitability if life could survive the initial sterilization period in deep underground refuges. The orbital mechanics challenges for white dwarf survival require engineering projects on planetary scales. Earth's current orbital distance would be far too remote to receive adequate heat from a cooling white dwarf. The habitable zone extends only 0.005 to 0.02 astronomical units from the stellar surface. Closer than Mercury's orbit around our current Sunday, achieving such proximity would require either moving Earth inward through gravitational assists or accepting tidal locking conditions where one hemisphere faces permanent daylight while the other endures eternal darkness. The tidal locking scenario could theoretically create habitable zones along the terminator boundary between permanent day and night hemispheres. Mathematical models suggest that atmospheric circulation could redistribute heat sufficiently to maintain liquid water in twilight regions, though the climate dynamics would create weather patterns unlike anything in Earth's history. Massive convective systems would transport heat from the day side to the night side, creating perpetual storms and temperature gradients spanning hundreds of degrees across relatively short distances. Recent research into extremophile organisms has expanded our understanding of life's possible limits under cosmic replacement scenarios. Deinococcus radiodurans can survive radiation doses 3,000 times greater than lethal levels for humans, while Pyrococcus furiosus thrives at temperatures exceeding 100 degrees Celsius using sulfur compounds as energy sources. Tardigrades can survive exposure to space vacuum, cosmic radiation, and temperatures ranging from near absolute zero to over 150 degrees Celsius, demonstrating that some life forms possess extraordinary resilience to environmental extremes. The discovery of life in Earth's deep biosphere has revealed ecosystems extending to depths where pressures exceed 1,000 atmospheres and temperatures approach 120 degrees Celsius. These environments remain isolated from surface conditions for millions of years, suggesting that deep crustal life could potentially survive cosmic replacement scenarios that sterilize surface and shallow subsurface environments. The total biomass in Earth's deep biosphere may exceed that of all surface life, indicating that our planet harbors vast reserves of biological activity independent of solar energy. Perhaps most remarkably, some extremophile organisms derive energy from radioactive decay itself, using radiolysis of water molecules to generate chemical energy sources. These radiotrophic fungi and bacteria could theoretically thrive in environments where cosmic radiation creates enhanced radioactivity, potentially finding expanded energy sources around neutron stars or in the aftermath of magnetar gamma-ray bursts. The psychological challenges for human survival would prove as daunting as the physical ones. The complete transformation of Earth's environment, the loss of familiar sky patterns, and the knowledge that technological civilization had ended forever would create mental health challenges unprecedented in human experience. Social structures would collapse as communication systems failed and supply chains disintegrated, leaving surviving populations isolated in underground refuges with limited resources and no hope of rescue. Yet against all odds, life's history on Earth suggests that some forms of biological activity could persist through even the most extreme cosmic catastrophes. The survival might not resemble anything we would recognize as familiar life, and it certainly would not include human civilization as we know it, but the fundamental chemistry of biology operates according to principles robust enough to function in environments that challenge every assumption about habitability. As we prepare to examine the precise mathematical boundaries between survival and extinction, the exact radiation doses, electromagnetic field strengths, and energy requirements that separate life from death in cosmic replacement scenarios, we carry with us the sobering knowledge that life's tenacity, while remarkable, operates within physical limits that can be calculated with the same precision used to predict planetary orbits or stellar evolution. 11. The physics of destruction. From the stubborn tenacity of extremophile bacteria clinging to existence in environments that mock the very concept of habitability, we now turn to examine the precise mathematical boundaries that separate survival from annihilation, the exact numbers that determine whether life endures or perishes when confronted with cosmic forces that operate according to rules written in the fundamental constants of physics itself. These are not abstract calculations confined to theoretical papers, but the quantitative measures of destruction calibrated with the same precision used to land spacecraft on distant worlds or predict eclipses centuries in advance. In this realm, death and survival become matters of pure mathematics, where the difference between existence and extinction can be calculated to decimal places that would make accountants weep. The universe operates according to physical laws so precisely defined that the moment of biological extinction can be predicted with the accuracy of atomic clocks. Tidal forces, the differential gravitational acceleration across an extended object, follow mathematical relationships established by Newton and refined by Einstein, creating destruction that unfolds according to equations as reliable as the